So today we are going to discuss about object detection. Just a small recap. You have learned about convolutions in the machine learning course. So how many here have taken the machine learning course? Most of you, right? So this is how a convolution operation works, right? You have an image on the left hand side. There is a kernel of size 3 cross 3 here, and the numbers which you see moving are the values inside of that kernel. And when you multiply each of those values with the image values and take a sum, you get the right hand side image, right? So that's how a convolution works. So let me ask you a simple question. Is convolution a sequential operation or parallel operation? So those of you think sequential can raise their hands. Parallel? Okay, so everybody knows that convolution is a parallel operation. We'll use this information in later of the slides. So let's start with something that we know already. You all are familiar with classification. How classification works is you pass this image into a CNN or any neural network, and then it provides you an probabilities for the number of classes that you have, right? And in this case, this is a car, so it is correctly predicting it as a car. Now, what is a detection problem? So in a detection problem, you will be given an image like this, and you are interested to find out this bounding box and the corresponding label. In this case, this is a car, and you see a correct bounding box. We see a correct bounding box around a pedestrian and another car, right? So this image shows that even if there are multiple objects with the same category, you would still be want to you should be able to detect them, right? So let's think a little bit about where to use the object detection over the classification, because you already know the classification technology. If you want to switch to object detection, you should have a good reason to do that, right? So I'll just pause for a few moments so that you can think about it. Okay, now let's see. So wherever you need a localization, which means that you are just not interested in what is the object inside the image, but where exactly the object is, right? This can come handy when you are building something like automatic driving system, right? Then you would like to know where exactly in the image there is an object so that you can take a decision accordingly. Sometimes you require counts of the objects. For example, you would like to count number of elephants from the satellite imagery. In this case, object detection is better method. In cases where you require the size and scale of the object as well. For example, you are interested in counting the fire events and also the area of those fire events. There could be more applications, but like we have just seen a few. Now let us see how can we convert the classification problem to a detection problem. In the classification, you may already have some training set. Like let us say you are interested in detecting the cars, then you may have a training data set which looks like this. First 3 images are of car, and let us say we are assigning class 1 to the cars, and then the last 2 images are of the background. So all we need to do is take some patch from this image and pass it to the classifier that we have, and it will provide us the classification, right? In this case, it is a background. We can take another patch, and if we happen to get this one, then we will get car as a prediction, right? Now we can use this method to do something called as sliding window detection, which means that we will use a fixed size window, and then we will convolve it over this image, and we will get the classification for each of those windows, and that way we will be able to detect an object. Yeah.
So in this sliding window, when we doing it and we classifying, so do we use a pre-trained CNN to classify these patches, or do we have someone manually annotating these patches and then train a CNN to classify these?
You can think of this as a task from scratch as well. Like you can also do a training from scratch, but you have to then provide the labels correctly for each of those patches. Like if you are doing the inference, you can use a pre-trained model as well, that will work. But let us say you don't have a model, you want to train from scratch, you can train as well.
You train on the whole image, or you train on these small patches? So
Yeah, so you have to like figure out like how exactly to provide the labels, right? Because you know that okay, you are doing the sliding operation, and then at a particular location you are going to get the car. So at that location you have to set that label, and accordingly, like if there are more objects, you can set those accordingly. So now you may have seen that this size of bounding box may not be enough for all the objects, right? So we may want to increase the size, and then we do the convolution again, and we can even choose a bigger box. So this way we can convert the classification task to the detection task. Is it the optimal way? Perhaps not, but we will see. So what could be the challenges with this method? Any answers?
Size of the box, because one box might be able to detect some smaller car, but if it's a larger car, then it won't be able to detect that.
Yeah, but in this case, we will select a range. Let us say you select a 2 cross 2 versus you select a 10 cross 10, and you just go over a for loop, just detect using them. Because you will have some idea like what could be the minimum size of the object and maximum size of the object. So that problem can be taken care of.
The image is large, so like it may be fit into two sliding boxes. So what are the like should we consider a center of mass of that object to detect like if that bounding box take that center of mass of the object, it will detect that that object is that.
Okay, so perhaps what you mean is like how do we ensure that the bounding box is exactly on the object or not, right?
Like if like there is a truck, so like multiple sliding boxes are required
Right.
for that object detection. So like if we slide those boxes and perhaps that sliding window which has that center of mass of the object or the center of the object, that only bounding box will classify it as a truck, and other rest
Yeah.
that will not classify it.
Yeah, so here because we are using a sliding window and we can choose a stride of something, so that way there is a possibility that multiple of those windows may detect the object also, right? But because this is a classification problem, you will get a probability also with this, right? So yeah, we can detect the objects, but like what are the challenges, so that if you try to use this method in practice, you will not be able to. What are some practical considerations? One is like as we have seen already, there could be duplicates, right? Like this box will select the box, select the object. This box may also, this box may also. So now, how do you select the optimal box which is correctly finding the bounding box of your object?
Can you set a threshold or something, the maximum area which is covered in the car? We can say that.
But you don't know the ground truth, right? So like at the test time, you don't know where the car is. So how would you choose that?
Taking
Average of all bounding boxes. Okay, in that case also it might not be the best one. Can you use some models knowledge to do this? Like wherever the model thinks that there is a highest probability of the object, maybe that is the best box to choose, right?
yes, that's what I was saying.
Yeah.
We can set a threshold the highest probability.
Okay, yeah, on the probability, yeah, we can set a threshold, or in another words we can say that we can choose a bounding box with the highest probability, right? Because choosing a fixed threshold may not always help.
That's what I was saying. Like in AISG, we set a threshold, and after that we consider it.
Right. So there is a concept called non-max separation which is used in the object detection. So we will see how it works.
Can also repeat the questions or the answers for the
Yeah.
not now, whenever
Okay.
you get-
Yeah. So then there is another challenge which is the computational cost, because you know that in recent times the classification networks, they are also growing big. So you cannot really afford to pass in each of these individual patches which are slided over the image into these big networks and get the classification out. So these are the two fundamental challenges, and now we'll see how we can solve them. Before that, let's get introduced to a terminology called intersection over union. This is useful in multiple ways. One is to check if your bounding box which is predicted is correct or not, and another use case is to check do the non-max separation, right? So how do we calculate intersection over union is like this. You see that there is a red box which looks like a ground truth, and then there is another box which is like a predicted box. So you take the intersection area between these two, which is in yellow, and then you divide by the union area, which is in the green, right? And this ratio gives us the intersection over union. So in practice, 0.5 is generally used as a good IOU, but based on your application, you can change this value. Now this comes handy when we want to do something known as the non-max suppression. Okay. So we will see how it works. These are all the predictions. Yeah, there is a question. Intersection over union. Okay. Yeah. Yellow box is the intersection between these two boxes.
What is, it is the box which model use or?
So the red box is the ground truth and the violet box, that is the prediction. Now you will find an intersection between these two. So that area is like used in the numerator. Then we divide that with the union of the total area in the denominator, and this ratio is intersection over union.
Previously, you told that during tests we don't have the ground truth, but then how with the testing phase is different?
Yeah, so that was for the non-max suppression. We will see how it works there. But in the test phase or in the during the evaluation, you know the ground truth. You know the exact bounding box so that you can check. Right? Similar to how you check the accuracy. Right? So let us say these are your predictions. For the right hand side object, we see there are 3 bounding boxes with different probabilities 0.6, 0.7 and 0.9. We see that 0.9 probability object is 0.9 probability bounding box is covering the object in the best possible way. So what we can do is we compute the intersection over union of this box with all the boxes which are present in the image. And then we remove all the boxes which have intersection over union beyond a threshold. Now that threshold is a hyperparameter that we use. So here we can see that this highlighted box is selected and the other boxes are discarded. Similarly, on the left hand side image, this box will be chosen and the other box will be discarded. So in the end, we will be remained with these 2 bounding boxes. So yeah. Yeah, this is not the ground truth. Yes, this is prediction only. So any doubts with non-max suppression?
How you are going to decide the threshold?
That is a hyperparameter. You can choose based on your application.
What will happen if there is some resolution issue or zooming in that image? Then the threshold will change and the outcome become negative.
Yeah, so as a human, like we have to decide that. We have to take a call on that. Okay, now we will discuss about the another problem, which is computational complexity. So one way to solve this problem is to convert the fully connected layers which are at the end of the classification network to a CNN. We will see how we can do this. Let us say you have an image of 14 cross 14 cross 3 and you use a 5 cross 5 kernel on top of that. The output will be 10 cross 10 and we are using 16 channels. So we will get 10 cross 10 cross 16 output. We apply a max pooling and get 5 cross 5 cross 16. And then we convert this to a fully connected layer, which means 16 into 5 into 5. We just flatten this array and it becomes 400 sized. Then you connect it with another fully connected layer of size 400. And at the end, you connect it with the 4 neurons and apply the softmax. Let us say this is a 4 class classification problem. In that case, the last layer size will be 4. This is how a classification network looks like. So till this point, we are continuing the same, but at this point we can say that, let us say at this stage, I am again using a 5 cross 5 filter here, right? So there is no stride, nothing. This will just flatten out into a 1 cross 1. And then I am using 400 channels here, right? So then I'll get something like 1 cross 1 cross 400. Now this is equivalent to this 400 sized vector. Then I can use a kernel of 1 cross 1 again and I'll get an output of 1 cross 1 cross 400. Here also 400 is the size of channels we are using. And finally, we can reduce it to 1 cross 1 cross 4, right? So any doubt in this relationship between these two? Yeah,
What is the point of using one cross one kernel?
we'll see in the next slide. Yeah. Right, so this part is just copied from the last slide. Now let us say your image size is 16 cross 16 cross 3. There are 2 pixels in the row and in the column additionally. Now you can think of this as an operation that like we continued in the upper part, and we will end up with 2 cross 2 cross 4, right? How this will happen is with the convolution, right? Here if you use a stride of 2, then you will move this window by 2 pixels on the right, and then you will go to the next row and do the same process. So with this process you will end up with 2 cross 2 cross 4. So now you have seen what we have done. Like with a single forward pass, we computed the class probabilities of 4 different regions in the image, right? We can use the same concept with a much bigger image, and if we do this, we will end up with 8 cross 8 cross 4, right? So which means that we have now checked each and every 14 cross 14 window of this image with stride of 2 or 1 probably, and we will get the final output, right? So this way we are not passing each of these patches individually into the convolutional net, but we have modified the network structure itself. Any doubts in this? Yeah, so the most important part is the second row. First row is clear, right? So in the second row what we are doing is the same operation that we did in the first row, we will do that convolutionally, which means window size is what you see in the blue. Then if you use a stride of 2, you can move 2 pixels to the right, right? And then it will also follow, and in that case it will correspond to this pixel here, right? And then when you go to the next row, it will correspond to this pixel, and then next it will correspond to this last pixel. Now you can do this operation with arbitrarily any size, and this size will correspond with that, right? I think it is clear. So this way we can just implement this algorithm to find out, like do this convolution like this and find out an object in the image without much of the computational overhead. Any doubt till this point? Okay, so now we are going to solve another problem which is like, here we have to try out each and every size of the bounding boxes to fit in an object, right? How can you avoid this problem and transform the problem completely, right? So that's where we will go towards classification with localization. So here let us say you are interested in doing the localization of this object also along with the classification. So what modification you need to apply to this network is that you are anyway outputting the softmax of 4. Additionally, you can predict 4 more numbers which are bx, by, bh and bw. So x and y are representing the center of the object, and bh and bw are the height and width of the object. Now the coordinate system is like this. The top left corner is 0 0, bottom right is 1 1, and we will scale this size accordingly. So in this case the 4 numbers may look like this. So if you train your network like this, then given a single object in your image, you will be able to localize it with an, maybe we can say, exact bounding box in this case. So here we have avoided the problem of checking a range of bounding boxes, and we are getting an exact bounding box by converting that to a regression problem. Right, so now how can we use this when there are more than one objects in the image, right? So we just expand this further, and then we define the target y as this vector. The first value here is the probability that an object exists in the image or not. The rest 4 numbers bx, by, bh, bw are representing the size and location of the bounding box, and then c1, c2, c3 are the probabilities corresponding to different classes, right? So in this case there are we are considering three classes: pedestrian, car, and motorcycle. For the background class, you will not need a C4 separately, because in that case your PC will be 0. Right? So there is an important change here, which is like we are differentiating between the class probabilities and probability that is there an object in the image or not. How this will come handy is when you define the loss function. We will see. So for this particular image, we know that there is an image, there is an object in the image. So we will put PC equal to 1. We will provide the corresponding BX, BY, BH, BW, and then because car is at a position 1, we put 1 at position 1, and then 0, 1, 0 will be the number. In the second image, because it is background, we'll put PC equal to 0, and then it doesn't matter what you put in the rest of the places, because you are not going to use it in the loss function anyway. Right? So does this convention make sense? Any question? So those are the coordinates we saw in the previous slide. So BX, BY is the center point of the bounding box, and BW and BH are the width and height. When you design your data set, that time you have to provide this information for training. So you would know exactly. Sorry?
It's always going to be a square, right?
No, not necessarily, right? You can change the BW and BH, and accordingly it will adjust. If you mean axis aligned, yes, it is going to be axis aligned. You cannot like use a rotated bounding box here.
So then if it is going to be a square of rectangle, we will need lesser amount of parameters.
Less, right? Yes. So because it is square or rectangle, you are able to identify this in 4 numbers. Yeah. Okay. Now let's take a look at how would you define a loss function for this. So this is a y vector that you have, and let us say your model has predicted a y vector, y hat vector here, which will also be of the same size. So if your y1 is 1, which means that your ground truth says that there is an object in the image, you want to apply some kind of loss between all of these different numbers in this y vector. But in case there is no object, you just want to minimize the loss between the first number. Right? That's how the loss would look like here. Any questions in the loss? This is not exactly the squared loss. Like you have to use another loss based on the like different things. Like in this case, it is a classification problem, so you would use the cross entropy. Okay. So if we put this everything together, then what we get is YOLO algorithm. So we have seen all the ingredients which are required to define the state-of-the-art algorithm which people use in current times. Okay, so we will see how the YOLO works. Let us say we have an image like this and we divide it in some fixed size windows. In this case, we are dividing it into 3x3 grid. And there are 3 classes: pedestrian, car, and motorcycle. We will define our y vector like this: PC, BX, BY, BH, BW, C1, C2, C3. But in this case, the y will be a 3x3x8 vector. Right? So why 3x3? Because for each of those windows, you want to define this 8 sized vector that we just saw in the previous slide. This is how the ground truth is given. Now, if we are talking about this particular window, then we will define the ground truth like this. First value is 0, rest of all doesn't matter. If you are looking at this particular box, you will give it like this. The first number PC is 1. You will provide some values for BX, BY, BH, BW, and you are saying that it is a car. Right? Okay, so now we will see like for what are some novel things that YOLO algorithm proposed which makes it a better algorithm. So if you notice that if the object is bigger than this window size, then it will create a problem. If you are restricting your BX, BH, like BX, BY, BH, BW to be inside of this. So they said that maybe it doesn't matter. You can just expand that outside the window also. right? So in this case, when you define your ground truth, you can give it in such a way so that even if the box goes out of the window, that is fine. Another novelty they used is something called as anchor box, which says that if you have an objects like this, where there is a car, where you would mostly use a horizontal bounding box, and then there is a woman where you would use a vertical bounding box. In such cases, if you just use a single prediction bounding box in a window, you will not be able to detect both of these objects, right? So when all we need to do is just repeat this 8 sized vector 2 times by an additional constraint that one of them has to be horizontal and another has to be vertical. So now we will get 3 cross 3 cross 2 cross 8, or we can just say 3 cross 3 cross 16. That will be the size of your ground truth vector. With the updated scheme, if we look at this yellow box, this will be our ground truth because there is no object. We will give PC equal to 0 at both places and rest of the numbers we don't need to give. For the second one of the predicted boxes will correspond to the object and another one will be rejected. So in the ground truth, we can decide which one we want to correspond to the horizontal one and which one we want to keep for the vertical, and accordingly we can give the ground truth. Right? So when you predict, at the prediction time, it will check the IOU with the predicted bounding boxes and correspondingly take the loss. So is there any doubt till this point?
What if both the bounding boxes are in same orientation?
You mean if both of them are overlapping?
Like you said, like one anchor box is horizontal, other one is vertical. What if both the anchor boxes are vertical or both the anchor boxes are horizontal? So how will it happen?
Yeah, in any case, because we have defined our condition like that we will take the maximum IOU box. So because you have the ground truth, you will be able to compute the IOU and then you choose the box which has the maximum IOU. Yeah. So this is something which like worked in the practice and they used. There is no necessity that you can only predict 2 boxes per window. You might be able to predict more also. And you might also put your own constraints on the how the box should look like.
Will you put any constraints to make the boxes vertical and horizontal, or is that just for explanation they show that we may end up learning 2 boxes, one of them is vertical and one is vertical?
I'll have
I
to
don't
check
know.
that. Yeah, I don't know at this point. Okay, so let's see the YOLO algorithm in action for this particular image. For each grid cell, we will predict 2 bounding boxes. So here we have predicted both the bounding boxes. Now we get rid of low probability predictions. So many of the bounding boxes are gone now. And then for each class, we will just use the non-max separation, where we choose a bounding box which has the maximum probability and discard all the bounding boxes having the IOU beyond the threshold that we define. Then we are end up with these 2 bounding boxes which look almost correct for the objects. Right? So this is the entire summary of the YOLO algorithm. Any doubt in this? Yeah.
In a single grid, there is multiple paths. How are we going to handle that?
Yeah, so they mentioned that those are the cases where this algorithm will fail. It will start failing. Now you have to understand that this is YOLO V1 and now there is a YOLO V11. So there are so many innovations which have happened, and in one of the innovation that constraint might also be solved, right?
So have they mentioned like what should be the grid size or ideal grid size?
In the original paper they chose 7 cross 7, but in the latest algorithms that they use, I'm not sure if they are using something dynamic.
So how can we decide the grid size? If I have some task, then how can I decide?
But to objectively answer your question, we can say that maybe it will not matter much, right? Because in this case, the bounding boxes can go outside the window also. So it doesn't matter that much, but you can just decide it based on your empirical observations. So any other questions? Okay. We'll also quickly see another algorithm called as RCNN, because this is also like parallelly being developed along with YOLO. But till this date, like YOLO is known for its speed, like, and that was the main like target in mind when people were developing YOLO, that we want to get something real time, because that time you might know that a lot of research was going for automatic driving car, right? So unless you are able to process this video stream which is captured by the car, I mean, there is no possibility of an automatic driving vehicle. So that's why a lot of research has gone into the speeding up this detection algorithms. You might find better algorithms which don't work as speedy as the YOLO algorithm, but which are better. That's also possible. So let's quickly see what is RCNN. So in RCNN, they use some segmentation algorithm to segment the image, and then they propose some regions. So in this case, on the right hand side, you can see there are some regions which are proposed, and then for each of those regions, they just use all the materials we have covered in the previous slide. For that, each of the bounding box, they will try to predict an object. So when the first RCNN algorithm came, they tried to propose the algorithms and then classify the proposed regions one at a time. That's why it was a very slow algorithm. In the next version, they used the convolution implementation to classify all the proposed regions at once. So here they have used the convolution to do the parallelization, and there is a algorithm called faster RCNN, where they use the convolutional network to even propose the regions. So another level of parallelization, and that's why it became even faster. Okay. So now let's see how we will evaluate such an algorithm. We will quickly see about true positives, false positives, and false negative. How would you get these numbers for the object detection? Now when you get these numbers, that is always class specific, which means you are computing this only for a single class. For this example, let's consider that class to be car. There are two hyperparameters while computing this. One is IOU, another is confidence threshold. For a car class, let us say there is a, okay, I think there is some problem. Yeah, so let us say there is a ground truth around this car, and then the predicted bounding box is also around the same. In that case, we will call it as a true positive. If the bounding box is around the person and then it says car, that means that is a false positive, right? And then if the algorithm is not able to detect this car, we will call it as a false negative. So as simple as this, and then you know the formulas of precision and recall to like compute these values from TP, FP and FN. Now one problem here is that you have to again decide what these hyperparameters should be, the IOU and confidence threshold. IOU is the one which is easier to pick, maybe 0.5 just works well in the practice, but confidence threshold you don't really know, like what is a good confidence threshold for your problem. That's why the community uses a metric called as mean average precision, which is nothing but the area under the precision recall curve, but just computed in a slightly different way. So to compute mean average precision, first we will compute something known as average precision, which is computed per class. So this animation shows you exactly that on the x-axis you get recall, on the y-axis you get precision when you draw the precision recall curve. Now you check that if you bin these things between 0 to 0.1 recall, what is your average precision? Then you check between 0.1 to 0.2, what is your average precision? Like that, if you do for all the bins, you will get you can do a summation of all these numbers and do the average. That will become your average precision. When you take a mean of AP over all classes, that becomes MAP. And when you compute this at a particular IOU threshold, that's where people use terminologies like MAP 50, MAP 5095. Right? So such terminologies are used. When we say MAP 5095, it means it is average of 50, 55, 60 like that in that till 95. So that way you get the MAP 5095. So this is about the metric. Till this point, any questions? In the assignments, you will be given to implement these functions as well. So you will get more exposure to this.
We are averaging the precision for every class.
Now first you compute the average precision
What's average
for each class.
for each class?
Yeah, so for each class you will get this precision recall curve separately. And then you just take a simple average to get the MAP.
Is OBB different from object detection? Like
Yeah,
you always
OBB is,
use-
yeah. So OBB is a slightly newer technology. Like there you need 8 numbers to describe a bounding box compared to 4 numbers.
So like it solves the problem of if the grid is like having two or more than two objects, it detects small.
In a way, yes, we can say that. You might have seen something like there are yachts parked very close to each other, right? And then if you try to use this kind of axis aligned bounding box, it's difficult to detect them. But if you use oriented one, it's easier. You can simply think of cars which are there in the parking slot, right? If they are at a particular angle and if you try to use an axis aligned bounding box, you will like end up discarding many of the bounding box in the non-max suppression itself. So in those cases, oriented bounding boxes help. We'll see in later of the slides how those things work. In the previous slide,
For the same class, there are two objects. So if model detects one and didn't detect one, then it will do where it's false negative or true positive.
so you always like do this true positives, false positive, or for predicted ones, right?
So it detected one, but
Yes, it detected one. So for that, we will call it, like if it is a correct one, we will call it true positive. If it is on the wrong class, we will call it false positive. And if there is an object but it is not detected, we will call it false negative.
here is two objects.
Yes.
50% is detected and 50% is not detected.
Yeah, so this one, let us say, is detected. And the bounding box and all is good as per the hyperparameters. We will call it a true positive. Right? And if this is not detected, we will call it false negative.
So it will be counted both.
No, like these two are counted separately. Right?
But that won't
That's
be
how it
predicted,
happens.
right? It won't be predicted by the algorithm itself. Let's say. Then how it will proceed. Like in that, let's say it's less than 0.5. Very less portion of the car is visible in the image.
Okay.
It doesn't get counted itself, so it's not get detected.
Now, like what gets counted and what not depends on your ground truth data set. Because you will be, to compute these numbers, you will need the ground truth, bounding boxes around each of these
Better
objects.
if it's as well during ground truth calculation.
Yeah, it depends on your application, right? Let us say you are just interested in detecting big cars. You're not interested in small cars which are like remotely visible. You will not put them in the ground truth. And if model detects that, you will count that as false positive. So this is like flexible as per your applications. Okay, so if this till this point, if there are no doubts, I'll discuss a little bit about one of our projects which uses object detection in practice. Okay. So this project is about detecting something known as brick kilns, which is a brick manufacturing industries from the satellite imagery. The motivation behind this is air pollution is a deadly problem and it kills 70 lakh people every year. And brick kiln emissions contribute 8 to 14% of this air pollution in South Asia. So while detecting the brick kilns, we have to choose a satellite imagery, and here is how you will see the comparison of 3 different resolutions. Sentinel-2 is completely free imagery. You can download it in any part of the world. It's available at 10 meter. Planet Labs imagery is at 5 meter. You have to create an account for education to get this imagery. And Google's imagery is proprietary, but you get a very high resolution imagery. So this is how the brick kilns look in each of these imageries. We will see a close-up look. So these are satellite views of the brick kilns. The left hand side technology is known as FCBK and right hand side is known as zigzag. The zigzag technology produces 40% less pollution. So in this entire project, what we are trying to do is see how many FCBKs are present, how many zigzags are present, and over time how many brick kilns have, let us say, converted from FCBK to zigzag, how many new zigzags have appeared, right? All of these things policymakers will be interested in. So here is what we were talking about oriented bounding box. So the this particular axis is known as axis aligned bounding box, and then this green box is known as the oriented bounding box. So in this you just need one additional parameter known as angle, because you already have the center point, height and width of the object. You just need to predict an additional parameter called angle, which will take care of the angle of the bounding box. So where this kind of bounding box will be important is, let us say you want to estimate the area of the brick kiln. Then your axis aligned bounding box is not doing a good job at this. Like if I just change the orientation of the same brick kiln, I will get different areas. But if I am using an OBB, I will almost get the same area in all cases, irrespective of the orientation. This is how we are using the annotation process. We developed our own tool, but there are also plenty of tools available if you want to create your own dataset. One famous tool is known as Label Studio, which you can install on your laptop also. So this is how we'll have to create a bounding box and then orient them based on the orientation. These are some of the data samples where we have annotated the images. For this project, we have created the dataset entirely from scratch. So first of all, we created an initial dataset of around 1500 total brick kilns from different parts of India to train the initial model object detector. For model, we have used the latest model from Ultralytics. You will use this in your assignments also. Ultralytics is company which is keeping track of these models, and they are also developing the YOLO models. So when we did some experiments on the initial datasets, this is how we get the results. So I am showing this table to just show you that how you can calculate and report the results for your problem. In this case, there are three categories: C, FCBK, FCBK and zigzag. For each of them, we are reporting AP here, right, that we saw in the previous slides. And then when we take a simple mean, we'll get MAP here. So in all the papers that you see about object detection, you will see a big tables looking like this.
What exactly happens in FCBK and zigzags? How the bricks are laid?
Yeah, so those are very specific details about the project. You can take it offline.
How the brick is laid, or we can say it from the beginning?
So in short, I can say that they are just increasing the time for the fire. The fire will keep moving inside the brick kiln. So they are just increasing that time so that more of the heat is utilized, and that's why it is more efficient.
So my question is, what exactly the YOLO 11 is capturing the pictures?
Okay.
So it is differentiating between the zigzag and
Okay, got it. So the question is that how are you able to differentiate between FCBK and zigzag? So if you see the FCBK, here there is an ovular shape at both ends of the brick kiln, and here it is exactly a rectangular shape. So that's one of the fortunate thing that we are able to identify because of this particular change. Let us say both of them had similar design, but it was another one was still efficient, we will not be able to do anything.
so
Right.
that means we need more high resolution satellite image. We cannot do with that satellite.
We have done some experiments with those as well. They are not that good, but they are not that bad as well. But it is obvious that if we use Sentinel-2 compared to Planet, results are not that good. Planet, we get better results. Google, we get the best results. But we tried these different satellite imageries because Google's imagery is proprietary. So in the talk of professor from Plaksha, you might have also seen, right? So when you have such imageries, it's difficult to publish because they are proprietary imagery. You can't use your models on them. For class projects, yeah, it is okay. You can use it.
Another problem also in case of 5 meter, this labeling is also a bit
shared data label.
Right, yes. To get a label, for a human also it might be difficult to identify the kiln technology and the kiln itself. So for that problem, we just annotated the high resolution imagery and transferred those labels onto low resolution imagery.
There's another point to Amod's question. So I think the general consensus is that we want. So if we can't see something, then you also expect the machine also to be not able to see. But that's not always the case. Machine can deal with pixels, etc. And if we have provided enough training data, you might be able to see something. Machine might be able to see.
Right. Yeah. So as a final outcome of this project, we were able to detect around 30,000 brick kilns across 5 states of India. And here is how the geographical distribution of brick kilns. In your assignment also, like when you do the solar plate detection, like there is a question where you have to geo-reference the images and objects. So there you are expected to make this kind of plots where you pinpoint the locations of each of the solar plates on the maps like this. Okay, so this is end of the slides. If there are any questions we can take, or I'll go to the notebook.
I had a question that we use object detection thing. Why can't we use object segmentation instead of that? Like, what's the difference? Like, I know the difference that we can get a perfect shape and all this. Like a project like Bricklin, we can use object segmentation. It would give good like output.
Yeah, right. So we can follow a philosophy like this. Like when I started the slides, I said that why use object detection when you already have classification? So then we argued that these are maybe some of the applications where object classification will not suffice. You will require detection. Let us say one of them is localization, another one is counting. Similarly, if you feel that for your project the object detection is not sufficient, you will require segmentation to compute some particular important property which is important for the project and go for the segmentation. Yeah. That is like subjective, like what's important in different projects. Based on that we can take a call.
So there is no difference like object detection and segmentation.
Yeah, there is a difference. Like in a very short summary, we can say that in segmentation you are trying to classify each and every pixel of the image, that it belongs to which class. And in object detection you are just trying to predict a bounding box. So I can say that object detection is much more constrained problem, right, compared to the segmentation. Now your question is like, why can't we use it for brick kilns, right? Let us say we are using segmentation and then it is putting some small segment in some area where there is no brick kiln. So it becomes harder for me to now take something as a single object and then mark it as a brick kiln. But in this case there are no such issues. We know for sure that there is going to be a bounding box. Either it will be brick kiln or it will not be brick kiln, right?
So just to conclude from that, the annotation process for segmentation is also much more expensive.
Yeah.
Segmentation is useful for that case where we need the exact same, like tumors.
Right. Yeah. So there could be some medical imagery where the problem is not at a particular location. It is at a different locations. You want to identify all those areas.
You plotted the last all those hints and classes.
Mhm.
Only true positives were plotted or even false positives?
These are all hand verified, which means whatever the model has predicted, we have hand validated them and only showing the ones which are correct. But for a large scale project, if that is not possible, you can also rely on the performance that you get on your test data set and then say that with this much probability my bounding boxes are correct. Okay, are there any other questions? So we'll go through a notebook which might become helpful when you are solving your assignment. Mostly we will use a library from RoboFlow called Supervision, and another library is Ultralytics and RoboFlow itself. So let me zoom in a little bit. First of all, we are downloading a dataset called as poker cards dataset. The syntax to download is like a same template for all the datasets that you download from RoboFlow. So just to mention that you can also go and check the RoboFlow universe where like lots of different datasets are available for object detection. So once we download the dataset, we can check the location and we can then explore the dataset. So here the location, the directory is arranged like this, that in the root directory there is a train, and inside of that there is images folder. Similarly, there will be validation and there will be test. Each of these folders will have images and labels, and in images you will have star.jpg, in the labels you will have star.txt, and all those txt files will have one-to-one correspondence with these jpg files, which means they will have exactly the same name as these images with a different extension. And all the txt files will have the annotations for these images. So those annotations are like mentioning where exactly are the objects in the image, and that is in something known as a YOLO format. You can go and check like later what's exactly the YOLO format. Now for Ultralytics models, there is something known as data.yml, which specifies some basic details about the datasets. Like here it specifies the classes. This dataset includes the cards from poker, and these are the different classes. Number of classes total we have is 52, as you all know. Okay, so now this is the syntax we can use to load this dataset using supervision. So we are calling supervision in short SV. So SV dot detection dataset from YOLO, you pass the directory where images are there, you pass the directory where labels are there, and then you pass the YML file path. Using these three, it will load all the dataset. Then we are just trying to visualize a single sample from this data. This image is coming from pillow. So when you call image.from array image, it just shows you the image here. Now because you have the ground truth, you can also annotate the images like this, and supervision provides simple tools to do this. You can use sv.box annotator here, and you call box annotator.annotate. You provide the image and you provide the annotations to it. You can see that we loaded the annotations from the first instance of the dataset. Once we provide this, we get the bounding boxes plotted like this. Now there are multiple annotators available in supervision, and we can use them all in combination. Let us say I want to add the label as well. Then I will use sv.label annotator, and I will pass the annotated image again into the label annotator. And in this case, now it nicely gives me the labels of each of the bounding boxes. Okay, so now we will see how to train the Ultralytics YOLO model. It's very straightforward. You provide the model that you want to use. Here I am providing YOLO 11M. M stands for the medium size model, which is around 35 MB in size. You call model.train and provide the path to your YAML file, which has all the other paths of your train, validation and test locations. You provide number of epochs you want to use. You provide the image size that you want to use. So if your images are not of this size, they will resize it to this size. Then once you start training, you will see a lot of details in the logs. This first para is showing you all the parameters or hyperparameters which are used to train this model. This is showing the architecture. It will also, if you don't provide the batch size, it will try to pick the batch size automatically. And if you want to provide, you can also explicitly provide that. You can also provide a parameter for like at how many epochs you want to keep running the model on the validation dataset and compute the metrics. Now here it shows the training process for each epoch. So when you don't provide that validation parameter, it will compute the validation matrix on each epoch. So this particular column is showing us MAP50 metric. After the first epoch itself, it achieved 0.3 of MAP50, 0.678594, and at the end of 10th epoch, it went to 988. So why it is able to do it so well in just 10 epochs is because this is a pre-trained model, and we are just now fine-tuning on a new data set. Once the training ends, it will show you the full metrics of the results for the validation dataset or the test dataset, I guess. Yeah, here it will show for the test dataset. So precision recall MAP50. So this particular row shows you the average MAP50 over all the classes. So there is a slight difference in the convention that we used. Like we called class specific MAP as AP, right? But here they are calling everything as MAP. So you should not get confused.
Quick question.
Yeah.
You said they're using a pre-trained model.
Yeah.
Can you tell on what categories is the pre-trained model trained on? And if you were to not fine tune and then just give these images, what is the expected output?
Right. So the axis aligned model of Ultralytics, they are all trained on COCO dataset, which is like released by Microsoft, and all the oriented bounding boxes, they are trained on DOTA dataset. So one thing which is like known is that such kind of classes will for surely not be there in the COCO dataset. So if you pass these images directly there, you will get no detections at all. But let us say if there is some object in the background which is there in the COCO dataset, then you will get a bounding box there. But that will be known as a false positive, as what we learned today. So now we will see how we can now use this model to predict on new images, and then in the end how we can evaluate. We can load the trained model from the paths. Like every time you train the model, it will create a new directory and save the model weights and all other things which are like produced during the training. We can use base.pt. This will be the model which is giving the best results on the validation dataset. And that's how you choose a model in any machine learning project. Once we get the trained model, first we are trying to load the test dataset with the same process we used earlier. We pick a particular image from the test dataset, and here we are calling .predict method from the trained model. When you pass this image, you get Ultralytics results, and then supervision provides the method to directly use this and convert it to supervision detections object. Once we get that, you can use all the supervisions machinery to do the visualizations. So we used these detections into these methods to visualize this. So in this particular image, we have got all the classes correct, and bounding boxes are also mostly correct. Now when you want to do the evaluation, we want to do this on each and every image of the test dataset. So here I am just running a for loop over the test dataset, doing the prediction, getting supervision detections and appending them to different lists. Now this is a recommended thing to do because sometimes you may not have any detections, and if you try to handle this in your own way, you may miss out some of the detections, and then one-to-one correspondence between annotations and detections will be lost. So that's why it's good to follow this boilerplate code. Once we get these two lists, we can just use sv.metrics.mean average precision. You call method.update detections list annotations list dot compute. This will compute the MAP results. MAP50 you directly get MAP50 95, and we also get the AP per class, which is of size 52, 10. So this 10 is giving us the values at different IOU thresholds starting from 0.5, 0.55, 0.6 up to 0.95. Right? So you will get 10 different IOU thresholds, and for each class it is giving us these values. So here, for example, we can just plot for each class what is the AP50 value, and we'll just need a single call of a matplotlib function. In this we can see that 5 op clubs is not getting a very good AP. So to do such kind of analysis, this kind of plots are useful. Okay, so I think that's the end of the notebook. And if you have any questions, you can.
Go to the evaluation phase.
Which one?
Evaluation phase start.
This one?
Say, evaluation phase.
Evaluation.
Start.
Okay.
Yeah. If you pass the any other model, this previous.
This one.
Yes, it's
Okay.
ASB detection reduction from here. If it pass, if you want to compute any other model map, then can you use that?
I think most of the models, like libraries which are out there, supervision supports them. But if you have developed something on your own, you have to just work around a little bit to convert that into a detections object.
I just send the images
Mhm.
and label path as euro format.
Okay.
And supervision can supervision compute it? Map and
So like the basic thing is you have to convert something into supervision detections object. Now either you do it using this kind of methods like from Ultralytics where you directly provide the Ultralytics results, or you can manually construct the detections object if you have a custom model. In both cases it will work then. Like it's like you have to first enter their ecosystem, then you can use all of the tools that they have. In your assignments you have some tasks where you are going to implement some of these things from scratch, so you will get fun of like doing this from scratch. Like this is a very simple, very straightforward notebook. Like if you are working on a project, this is good enough. Okay, so any final questions?
Okay, let's thank the speaker.